welcome to the 20th lecture in this series. So I was in the midst of a small computation last time. I wanted to show that the notion of a differential of a smooth map between manifolds coincides with our earlier notion of derivative when interpreted suitably. So in other words, let's start with a smooth map between Rn and Rm. We already have the classical derivative, and then we have this new derivative dfp. And the claim is that when we identify Rn with TPRn via this natural isomorphisms, then this equation holds. To check this, as I said, if we start with V in Rn, phi PV will land up here and then dfp will land here. So in other words, what I get this thing here is actually a derivation on Rm. So I have to see its action on a C infinity function on Rm. So I took alpha. So let it act on alpha. Now, and that, so let's unravel this. dfp acting on phi PV alpha is what I have here. Well, phi PV acting on alpha, as I've mentioned earlier. So phi PV alpha is the directional derivative d by dt alpha of p plus tv. I don't need this bracket, at t equals 0. That's what that's a definition. And we also know that this is the same thing as d, the usual derivative, right. So where was I? Yes. Yeah. So this is, one could write this in a couple of different ways. This is the directional derivative of alpha in the direction this, and that is the same thing as, now using my new notation. My new notation for the classical derivative, I use capital D. So capital D of alpha at the point P acting on V is what I have. This is one thing, but this is something we'll use later on. But let's go back to this, what I have here. We know that the differential of a smooth map in the abstract sense is given by, so this is going to be I think I kind of didn't write it correctly here. It's not quite this D, the bracket should not come here. Right, the bracket should come here. So really I'll use this, but on the not at this stage. Let me erase that. I don't need it at this stage. So this is what I have, alpha is, and I know that this is the same thing as phi PV of, well, alpha composed with F. What is this? This now I'm going to use the definition of directional derivative. So this is just the directional derivative of this function along the direction v. So I know that this is phi p v acting on alpha composed with f is just the directional derivative d by dt of alpha composed with f acting p plus tv at t equals 0. And I also know that this is the same as the classical derivative of alpha composed with f at the point P, and then acting on V. So at the in the end, what I get is going, now I'll just plug it back in here. So what I get is the left hand side of this equation, let's call it star, LHS, when acted, of course I have to act it on V and alpha, then what I get is this, exactly this d alpha composed with f at P of V. What about the right hand side? Right hand side is d right hand side is phi at f of p phi at f of p, and then I have dfp composed with. Now the whole thing should act on V, and then eventually it should act on alpha. This is phi of f of p dfp acting on V acting on alpha. And what does this this is right, and again using the same logic. So if I want to see what just like I had this here, if I this is phi at the subscript f of p of something something is equal to, this is the same thing as d by dt of so essentially I have to just take, so alpha, the starting point is f of p and the vector is t times df of pv at t equals 0. And what does that give us? Let's see. So this is the same thing as, right, so this is alpha d alpha at the point f of p acting on the vector df of p of v. Well, if you notice this expression here and this expression here, they are the same by chain rule. So this, which is equal to, and this chain rule that I'm talking about is the classical chain rule. Chain rule classical. So that using the classical chain rule, we see that everything works out, and the new derivative, new differential and the old one are related in the expected way. Now let me illustrate. So far it's been somewhat abstract. Let me illustrate all this with some examples. So first thing is, now I said, before I move to examples, I should add one more very important thing. The first thing is I said that the proof shows that something like this happens. The other thing is that the second point is that if P belongs to M and U phi is a chart, this is something very important for computations, chart containing P, we get a basis for TQM for all Q in U. So this is my M, this is U. So pictorially, sort of at every point I have a basis for the tangent space. And that basis is essentially, so we saw that this chart map phi is a diffeomorphism. Therefore, it's set up a correspondence between tangent spaces here, isomorphism between tangent space here and tangent space here. So we get a, namely, so if I want to get a basis for TQM, I know that the derivative d phi is going to map it to the tangent space to this. So this is U1, which we identified with tangent space to Rn itself. And we know what natural basis for tangent space to Rn is, namely the derivations corresponding to partial derivatives along the E1, E2, En directions. So namely, I look at d phi. So this is the point Q and this is phi of Q. D phi inverse at phi of Q then I look at this derivation d by dx1 at phi of Q. This is one single vector, and so I'll get n vectors like this: d phi inverse phi of Q d by dxn phi of Q. So this we have a natural basis for the tangent space of any open subset of Euclidean space, namely the partial derivative operators derivations, and using these derivations I can sort of pull them back via d phi inverse and get a basis. And I know that d phi is an isomorphism, therefore this will continue to be a basis. So this is very important, and usually it's denoted, one omits this d phi inverse etc. Usually one just writes del by del x1 etc. So this is the usual notation for the basis. Of course, one must keep in mind that these operators del by del xi are actually derivations defined on C infinity functions in Rn, not on the manifold, but it's sort of cumbersome to write all this lot of notation, so one just writes it like this. Right. Now let's move on to some examples of differentials and tangent spaces. So as we have seen that first is the trivial case. So if V is a vector space, now a vector space of dimension n, let us say, as such it does not have a topology, but what we can do is let any basis of V will give an isomorphism to Rn, since it has dimension n. So in particular we get a bijection from V to Rn. Now what one does is you just declare this, the topology on V is just the pullback topology from Rn. So in other words, declare a set to be open if and only if phi of that is open in Rn. So you force this phi to be a homeomorphism, and then of course it becomes a manifold as well with a single chart, namely the chart being phi itself. So you get a manifold structure in a trivial way. What we have seen is that if U contained in V is open, then TPU is isomorphic to TPV, which is isomorphic to Rn. We really don't actually, and in fact it's better to, one can set up an isomorphism with V rather than Rn. So the point is that one normally doesn't, even though there is an isomorphism involved, one doesn't think of the isomorphism. So in other words, any tangent vector to U, we don't distinguish between a tangent vector to U and tangent vector to V. After all, we saw that the only difference is that tangent vector to U will act on all C infinity functions on U, while tangent vector to V will act on all C infinity functions on which are defined on V, it's the larger set V. But we saw that one can go back and forth between the two, because to see the action of a derivation on a C infinity function, all that matters is the value of the C infinity function close to the point P, and because of that one doesn't distinguish. Now what about this TPV is isomorphic to V? I don't want to go via Rn to see this. In fact, directly one can see that TPV is isomorphic to V. So, and the isomorphism is exactly the same as what we talked about earlier. So V, so in order to see this, I start with an element of V, capital V, and I define a derivation. So let f belong to C infinity V. So you define V of f. The definition is exactly like in the Euclidean case, d by dt f of p plus tv, and then t equals 0. The good thing is that this f of p plus tv is just a real valued function of a real variable. One can forget about the intermediate vector space, and this derivative is in the usual classical one variable calculus sense. So, and the point is that this gives an isomorphism between V and TPV. I don't have to specifically mention Rn in the process. And right, so as specific examples of this, one can take V equal to the space of n cross n matrices, MNR. This is isomorphic to the vector space Rn squared. And what all this shows is that if we regard MNR as a manifold, it's just a vector space, then the tangent space at any point, a point in MNR is a matrix, this just can be identified with MNR itself. And it has an important open subset. Let U equal to GLNR, which is a set of matrices A in MNR, such that det A is not equal to 0. And this U is open since the determinant function from MNR to R is continuous. In fact, it's just a polynomial function, and U is nothing but, so just did this function det inverse of the interval minus infinity to 0 union 0 to infinity. So this is an open disconnected open subinterval of R. It's a continuous function, so the inverse image of an open interval would be open. So I get an open subset here, and this is a manifold as well, since it's an open subset of a vector space. And our discussion above shows that the tangent space to any point to GLNR is in fact can be identified with the bigger vector space MNR. So let's keep these two things in mind. Right. So the other example that I want to talk about is, let's look at a product manifold M1 cross M2, M equals M1 cross M2. Let's take a point P. Well, a point P will have two coordinates, P equals P1 comma P2, P1 in M1, P2 in M2. So this point P is in M. I want to look at the tangent space at P. TPM. The claim is that I want to claim that this is isomorphic to TP1 M1 direct sum TP2 M2. And this isomorphism can be described as follows. So we have the projection maps pi1 from M to M1, pi2 from M to M2. If I look at the derivative of the projection d pi1 at the point P, this would be a map from TPM to, well, it would be the tangent space at pi1 of P. Pi1 of P by definition is P1. So it's TP1M, and here it would be T pi 2 of P would be a map from TPM to TP2 of M. The claim is that, so if I combine these two projections, I'll get this isomorphism that I'm looking for. So I'll define a map alpha from TPM to TPM1 direct from TP1M1 to TP2M2 as follows. Alpha of a vector V is, I'll just do d pi 1 at P of V, d pi 2 at P of V. The claim is that this is an isomorphism, and this is quite easy to see. It's actually enough to check that, since we already know that the dimensions are of the right sizes. So this, note that dimension of the left hand side TPM is the same as dimension of the right hand side. So it's enough to check it's injective or surjective. So, or one can directly check it's both injective and surjective. See, the thing is that, so maybe I will leave it as an exercise to check that. One can check that. Easy to check that alpha is injective and surjective. So let me stop here. Maybe next time I might return back to this, but we'll stop here today. Thank you.